In this video, we're going to learn all about gas laws. So, gases are everywhere in real life. Gas is what inflates the tires in your car, inflates all of the different balls we play sports with. It's in balloons. It's what inflates an airbag if you get in a car accident. Gases are everywhere. There are certain properties of gases. They are the highest energy of all states of matter. And there is a lot of free space in gas. Unlike a solid where it's your atoms taking up a majority of the space, in a gas it's actually empty space that takes up a majority of the space. Gases can be expanded infinitely to whatever size their container is. They're going to fill those containers uniformly and completely, and gases diffuse and mix rapidly. So unlike if you're trying to mix like sugar and water and it might take a little while, gases mix incredibly quickly. So there are some variables we're concerned about when we're talking about gas laws. So gas properties can be modeled using math, and that model depends on a few things. V, which is the volume of gas, which we do in liters. T, which stands for temperature, and it is in Kelvin. Now, I know some of you are going to think that degrees Celsius is good enough, and if both of your units are in degrees Celsius, it's fine, but it is not. All temperatures in this entire unit must be in Kelvin. No exceptions, absolutely none. We have N, which is going to be our amount, and that's in moles. P is pressure, which we do in atmospheres, and then R is the universal gas constant, which is 0.0821 liters times atmospheres divided by moles Kelvin. Which brings us to something called kinetic molecular theory. So kinetic molecular theory is a theory that describes the behavior of gas particles, and there are 5 parts to this theory. The first one is that gases consist of tiny particles. These are either atoms or molecules. These particles are so small compared to the distance between them that the volume, the size of the individual particles, can be assumed to be negligible, so basically zero. These particles are in constant random motion, colliding with the walls of the container. These collisions with the walls cause the pressure exerted by the gas. So that's actually how a balloon blows up. When we are blowing up a balloon, it's actually the pressure of our air molecules hitting into the side of a balloon that blows it up. The particles are assumed to not attract or repel each other, so they're kind of indifferent. And our last part of kinetic molecular theory is that the average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. Once again, all of our temperatures always needs to be in Kelvin for this unit. So 2 vocabulary words you might not be familiar with are diffusion and effusion. So diffusion is the gradual mixing of molecules of different gases. So I want you to think about a person wearing perfume walking into the room. The person at the desk closest to where that person walked in from is going to smell that perfume the most. Meanwhile, the person farthest away from the door is going to barely smell the perfume at all. And that's because the perfume is slowly diffusing and mixing with the air in the room. So the person closest to the door is getting it first. Well, since it's a slow process, it's not getting to the person farther away until later. Effusion, on the other hand, is the gradual movement of molecules through a small hole. So I want you to think about a tire on a car with a small hole in it. What happens to the air in the tire? Well, your tire eventually goes flat even if it's a small hole, and that's because the air is effusing out of your tire. So STP stands for standard temperature and pressure, something we've talked about before. And gas behavior changes when the temperature and pressure are changed. And this is the reason we actually have a standard temperature and pressure, is because of gases. So STP allows us to compare different gases to each other. For this unit, standard temperature is 273 Kelvin, and standard pressure is 1 atmosphere, which you'll see abbreviated as ATM. At STP, 1 mole of gas occupies 22.4 liters of space, which is something you learned about earlier in the semester when we were doing stoichiometry. As far as temperature is concerned, temperature is a measure of average kinetic energy. In the real world, temperature can be measured in Fahrenheit like we do in America, or Celsius like they do in Europe, or Kelvin, which is pretty much only used by scientists. Once again, every problem this unit needs to be in units of Kelvin for temperature. Sometimes, though, you are going to be given a temperature in Celsius, and you're going to have to convert it to Kelvin, but it's a super easy conversion. You just take what your Celsius number is and add 273, and you get your Kelvin temperature. Now, you might be wondering where 273 comes from. That seems kind of like a random number, Miss Hinkson, but it's because matter cannot be cooled lower than negative 273 degrees Celsius. So we call this temperature absolute zero, and that is 0 Kelvin. So that means negative 273 Celsius equals 0 Kelvin. So whatever temperature we have in Celsius, we add 273 to get it to Kelvin. Once again, temperature at STP is 273 degrees Kelvin. So pressure was another factor that we talked about. So pressure is how often and how hard molecules collide with the container they are in. Atmospheric pressure is measured with a device called a barometer, and you can see a picture of a barometer on the side. So mercury is used in barometers, Hg on the periodic table, and it rises in this tube in the center until the force of the mercury down balances out the force of the atmosphere pushing up. It works kind of similar to a straw in a drink. So the column height measures the pressure of the atmospheres. Like thermometers, there'll usually be measurements going on here. So we have lots of different units of pressure at STP. You have 1 atmosphere, 1 atm, which is what we use. But that 1 atm equals 760 millimeters of mercury, which we get from the barometers actually moving mercury by the millimeter. 760 torr, 29.92 inches of mercury, 14.7 pounds per square inch, which we abbreviate as PSI. So if you've ever seen PSI somewhere, that's what it's talking about. 101.3 kilopascals, kPa, and about 34 feet of water. You need to be able to recognize these different units of pressure, and we will be using these values as conversion factors in an upcoming slide. And you need to be able to convert between these. So let's look at some pressure conversions. You are asked, what is 475 millimeters of mercury expressed in ATM, atmospheres? So we take our number from our problem, 475 millimeters of mercury. We learned on the previous slide that 760 millimeters of mercury equals 1 atm. So we multiply the top, divide by the bottom, and we get 0.625 atm. What about the pressure of a tire is measured as 29.4 psi? What is this pressure in millimeters of mercury? So we take our number from our problem, and if we look on the previous slide, we find that 14.7 psi equals 760 millimeters of mercury. Once again, multiply the top, divide by the bottom, round to our 3 sig figs that we have here, and we get 1520 millimeters of mercury. Now I want you to pause this video and try these two on your own. Use the conversion factors you learned 2 slides ago in order to answer these questions, and use the examples on the previous slide to help you. Unpause this video when you come back. So you were asked, what is 2 atm expressed in torr? So we take our 2 atmospheres. 1 atmosphere equals 760 torr, and that gets us 1520 torr. As far as the pressure of a tire is measured in 32.0 psi, what is this pressure in kPa? 32.0 psi, we know that 14.7 psi equals 101.3 kPa, so we calculate that to be 221 kilopascals. So this may surprise you, but the air you are breathing right now is actually 78.08 nitrogen. It is only 20.95% oxygen. There's actually just less than 1% of argon and a very, very small percent of carbon dioxide. Each of those gases exert a certain amount of pressure that you can see in that column of partial pressures at STP. Well, the total pressure in the air is equal to the sum of all of the partial pressures by each gas in the air. So that means our pressure of air is equal to the pressure of each of those gases individually added together. So if we add all of those partial pressures together, we can get the pressure of air. Which brings us to Dalton's law of partial pressures. And his law states that the total pressure in a container is equal to the sum of the partial pressures of each gas within the container. So pressure total equals the pressure of all of the parts added together. As an example, what is the total pressure in a flask containing hydrogen peroxide, H2O2, that breaks down to water and oxygen? Well, if our water is 0.32 atmospheres and our oxygen is 0.16 atmospheres, we just add 0.32 and 0.16 and find out that our total pressure is 0.48 atmospheres. Now I want you to read these two examples and try them on your own. Unpause the video and come back once you are finished. All right, so we are told that oxygen and chlorine gas are mixed in a container with partial pressures of 401 millimeters of mercury and 0.639 atmospheres respectively. What is the total pressure of this container in atmospheres? That in atmospheres was a hint for you because you needed to convert our 401 millimeters of mercury to atmospheres before you could actually solve this problem. Once you converted it, just like you would have done on one of our previous slides, you should have gotten the answer of 1.17 atmospheres. If you didn't, try converting the millimeters of mercury again. That's probably where you got wrong, and then add our two numbers together and see what you get. As far as example 3 is concerned, you're told container A contains a gas under 3.24 atmospheres of pressure, and container B contains a gas under 2.82 atmospheres of pressure, and container C contains a gas under 1.21 atmospheres of pressure. If all of these gases are put into container D, what would the pressure be in container D? This one was actually simpler than example 2 in that you just had to add those things together and get an answer of 7.27 atmospheres. We have a bunch of other gas laws to learn. Up first is Boyle's law. And this lovely gentleman right here is Robert Boyle. He was the son of Earl of Cork, Ireland. So his law was this little thing right here. If it doesn't make much sense to you, that's okay, because what it meant was pressure and volume are inversely proportional if moles and temperature are constant, meaning they don't change. So for example, when P goes up, volume goes down. Why is that? Well, if we look at this picture, it makes a lot of sense. If we have a certain pressure, we have this volume. But as the pressure increases, our volume gets smaller and smaller. So they're inversely proportional. So his law boils down to P1V1 equals P2V2, where our number of moles and our temperature are going to be held constant. So they don't factor into this. Let's look at a Boyle's law practice problem. So we're told a sample of oxygen gas occupies a volume of 250 milliliters at 740 torr pressure. What volume will it occupy at 810 torr? So first we identify our variables. We know that V1 is 250 milliliters and P1 is 740 torr. We don't know our volume, V2, which is what it's asking about, but we know that our P2 is 810 torr. So we use our formula, P1V1 equals P2V2, and we set it up. Then we just need to get volume on a side by its own, and rounding to the correct number of sig figs, all of our answers in our problem had 2, we get 230 milliliters. Next law up is Charles' law, and this is Jacques Charles. He actually also isolated boron and was known to be quite the balloonist. So this was his law, and what he said is that volume and temperature are directly proportional, meaning they increase together, they decrease together. And if you look at this picture down below, it explains why. If you put a balloon in ice water, it's going to get smaller. Its volume will get smaller, just like its temperature got lower. Meanwhile, you put a balloon in boiling water, it's going to get larger, just like the temperature of the water got larger. So his is V1 over T1 equals V2 over T2, where in this case, number of moles and pressure are being held constant. Let's look at a practice problem for him. So you're told a sample of nitrogen gas occupies a volume of 250.0 milliliters at 25 degrees Celsius. What volume will it occupy at 95 degrees Celsius? Now, before you jump in and identify your variables, something should be tickling in the back of your brain about seeing that Celsius. Oh yeah, it's that all of our temperatures need to be in Kelvin. So before we move forward, we have to get those 2 Celsius temperatures into Kelvin. So we identify our V1 as 250.0 milliliters, and we convert our T1 to Kelvin by taking it and adding 273 to it to get 298 Kelvin. We still don't know our V2, and we convert our T2 to Kelvin as well. Once we've done that, we just need to set up our equation where V1 goes over T1, and it equals V2 over T2. I recommend cross-multiplying and then dividing, but you can really solve this problem any way that gets V2 on its side by itself. And we get 309 milliliters for this case. Our next gas law is Gay-Lussac's law. That is him right here, looking dashing as always. And this was his law. And he said that P and T are directly proportional. They increase together, they decrease together. And if you look at our picture Y, it's kind of explaining. As our temperature increases, our pressure is going to increase because molecules are moving faster, creating more pressure. In his law, number of moles and volume are going to be constant. So let's take a look at an example problem for his law. He says a sample gas has a pressure of 75.0 kilopascals and 0 degrees Celsius. The pressure is increased to 225 kilopascals. What is the new temperature? As we're identifying our variables, you should remember you need to convert that Celsius to Kelvin. So we have 75 kilopascals as P1. 0 degrees Celsius becomes 273 Kelvin. And 125 kilopascals is our P2. So we plug it into our equation. Once again, I recommend cross-multiplying and then dividing, but choice is yours how you want to handle it. And you will get your temperature to T2 as 455 Kelvin. So these laws can all be put together in what is called the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. Now, as far as equations you'll be given, I will only be giving you the combined gas law. I won't be giving you each person's law individually. But remember, you can just cross out what you don't need in the combined gas law to get all of the other parts of it. But still in the combined gas law, our moles are being held constant. Let's look at an example using the combined gas law because you can use all of the parts of it. So a gas occupies 3.0 liters of space at 1.5 atmospheres and 20 degrees Celsius. If the pressure is increased to 2.5 atmospheres and the temperature rises to 30 degrees Celsius, how much space will this gas occupy? So we do our setup. Remember, the Celsius needed to be converted to Kelvin. That's where these two numbers came down here. We isolate our V2 on a side by itself, and we get 1.9 liters. So Avogadro, yes, Avogadro's number guy, had a hypothesis. And his hypothesis was equal volumes of gases at the same temperature and pressure have the same number of moles. Basically saying that volume and number of moles are directly proportional. They increase together, they decrease together. That makes sense. The larger the volume, the larger your number of moles are going to be. In his hypothesis, temperature and pressure are constant. So let's look at Avogadro's hypothesis practice problem. So suppose we have 12.2 liters of a sample containing 0.50 moles of oxygen. If all of this oxygen is converted to ozone, what is the new volume of our gas? So we're given V1 and we're given N1, and we know we're solving for V2 because the question is what is the new volume of gas, but you're going to have to use your buddy's stoichiometry in order to figure out how many moles of O3 you have. You're going to use your N1 and then use our mole ratio found in our equation to convert it to 0.33 moles of O3. Once you have all of that, you just set up your equation, cross multiply and divide to get your volume of 8.0 milliliters. Now remember, if you aren't getting any of these answers correct, you really need to go back and look at the problem and try again. Which brings us to our last gas law, the ideal gas law. So an ideal gas is a hypothetical gas that exactly obeys the ideal gas law. The thing is, no gases are actually ideal, but we treat them as ideal so we can do calculations. The ideal gas law is PV equals nRT, which you'll hear a lot of chemists refer to as PivNert, because when you put all the letters together, that's what it says. It's how I remember it. You will be given this equation as well. Remember, R is the universal gas constant, so R equals 0.0821. All the rest of them, except one, will be given to you in your problem, and you just have to solve for whatever one is missing. You'll be given R as a constant on tests and quizzes as well. You don't have to memorize that number. So let's look at an ideal gas law practice problem. You are asked how much space does 1 mole of oxygen occupy at STP. So our pressure is 1 atmosphere because that's the standard pressure at STP. We know we're looking for a volume because that's what space means. Our N is 0.00 moles. R is a constant, that number can't change. And STP temperature is 273 Kelvin. You should have known the pressure and temperature. I'm not going to give you those on test. You have to know what those numbers are at STP. So then we set up our problem, and we're trying to get V on a side by itself, and once we do, we get V equals 22.4 liters. If that number looks familiar, it's because 1 mole of any gas equals 22.4 liters of that gas. Wow, that was a lot. And I know over the course of all of these slides, it can really feel like it's a lot. So this is kind of a summary of all of the gas laws. Now, I'm not going to fill this table in for you. When I click the next button, it's not going to go to next. I want you to go over your notes, and I want you to fill in all of these boxes. This is going to be a great summary chart for you, and it's really going to help you on your note check. So go back through your notes and fill in everything here. If you have this blank, you're not using your notes on your note check. You can pause this video and come back when you're done, but like I said, I'm not going to give you the answers. But I do have one more slide. This is what you will be given as your formula sheet. So I will provide you with all of these things as far as on a test or quiz, so you don't have to have these things memorized. But if it's anything not on here, it is fair game for tests and quizzes, so make sure you know it. All right, that's all I got for you. Come in to class with any questions that you have, and I'll be glad to help you out.